The universe was born in fire and then went silent for 1 billion years. This was the cosmic dark ages, a profound era of darkness between the Big Bang's afterglow and the first starlight. Why does this mysterious period hold the key to everything we see today? By the end of this journey, you will understand 30 groundbreaking theories that are trying to crack this ultimate cosmic code. We will explore if the first stars were made of dark matter and what colossal black holes were doing in the emptiness. What do you think illuminated the cosmos after its long, deep night? Our starting point is a timeline, a cosmic storybook we call the Standard Cosmological Model. This is the baseline narrative, the fundamental chronology of the early universe that scientists use as their measuring stick. According to this model, the Dark Ages officially began about 380,000 years after the Big Bang. This moment was marked by a profound cosmic event, the release of the cosmic microwave background radiation, which was the universe's final shout of its fiery birth before it fell silent. After that light faded, the cosmos became a place of profound simplicity and darkness. It was not empty, but filled with a vast, cooling fog of neutral hydrogen and helium gas. There were no stars, no galaxies, no sources of light whatsoever. For nearly 1 billion years, the only force at work on large scales was gravity, patiently and relentlessly pulling these vast clouds of gas together. This slow cosmic gathering took hundreds of millions of years, a patient buildup of pressure and density, setting the stage for a dramatic finale. This theory gives us our fundamental clock, the established timeline against which every other, more exotic idea must be tested. It tells us that the end of the darkness was not a sudden accident, but the inevitable result of gravity's persistent pull. But that simple cosmic fog was not alone in the darkness. An unseen architect was already at work, laying the foundations for everything to come. This is the second theory, the crucial role of dark matter. While the neutral hydrogen gas drifted slowly, another, more mysterious substance was already clumping together with incredible speed. Dark matter, the invisible scaffolding of the cosmos, does not interact with light at all. It feels gravity, but it is immune to the pressure of radiation, which had been keeping normal matter spread out. This gave dark matter a massive head start. While the primordial gas was still smoothing itself out, dark matter was collapsing into an immense cosmic web, forming vast, invisible structures called halos. Think of these halos as deep, gravitational potholes forming in the fabric of space itself. They were silent and unseen, but their pull was immense. These dark matter halos became the universe's first skeletons. They provided the gravitational anchors, the traps necessary to catch and concentrate the wandering hydrogen gas. Without these pre-built wells of gravity, the thin gas might have simply continued drifting forever, never achieving the density needed to ignite a star. The formation of the very first proto-galaxies did not begin with a cloud of gas deciding to collapse. It began when a cloud of gas fell into one of these pre-existing dark matter pits. The gravity of the invisible halo pulled the gas in, compressing it, heating it, and finally making star formation possible. So dark matter was not a passive bystander in the Dark Ages. It was the active director, the hidden force that accelerated the entire process. It built the stages upon which the first stars would eventually shine. What if dark matter behaved differently? Could its unique properties have allowed strange, dark stars to form first, shining with a ghostly light we can barely conceive of? This cosmic fog, however, left behind a ghostly fossil record, and we have learned to read its pages. The key lies in the light from the most brilliant beacons in the distant universe, quasars. As the intense beam of a quasar journeys across the cosmos towards our telescopes, it passes through the remnants of that ancient hydrogen fog. The neutral hydrogen gas from the tail end of the Dark Ages does something very specific to this light. It absorbs a very particular color, a specific wavelength known as Lyman-alpha light. When astronomers finally catch this quasar light and spread it out into a rainbow-like spectrum, they do not see a clean, continuous band of color. Instead, they see a barcode, a dense series of dark absorption lines, each one a scratch made by a separate cloud of primordial hydrogen that the light passed through on its long journey to us. This is the Lyman-alpha forest. The closer the lines are packed together, the more clumpy and structured the gas was in that region of space. By meticulously decoding this barcode, scientists can perform a kind of cosmic archaeology. They can map the density and distribution of the universe's neutral gas, revealing how the invisible hand of dark matter was already sculpting the cosmos into a vast web. This forest of lines is the direct imprint of a universe stirring in its sleep, a universe where structures were quietly, darkly, forming hundreds of millions of years before the first star ever woke up to announce the dawn. But that ghostly barcode of light is not our only way to peer into the darkness. There is another signal, a whisper from the hydrogen fog itself, that could reveal the entire cosmic movie of this era. This is the fourth theory, the promise of the 21-centimeter line. The neutral hydrogen gas that filled the Dark Ages universe was not completely silent. Its solitary atoms, each a single proton with a single electron, occasionally perform a tiny quantum mechanical flip. The proton and electron, each spinning like a tiny top, can suddenly shift from spinning in the same direction to spinning in opposite directions. This minuscule event releases a very specific amount of energy, a photon of light with a wavelength of exactly 21 centimeters. This is the hyperfine transition, a faint but steady heartbeat from the primordial cosmos. For hundreds of millions of years, the entire universe was humming with this 21-centimeter radio whisper. Theorists realized that if we could somehow build a telescope sensitive enough to detect this ancient signal, we could do something miraculous. We could map it by observing how the signal's intensity changes across different parts of the sky and at different frequencies, which correspond to different distances. We could assemble a three-dimensional map of the universe during its darkest chapter. This would not be a single, static picture. It would be a cosmic movie showing us the hydrogen fog in motion. We could watch as the first invisible dark matter halos began to pull the gas into denser clumps, creating the first cosmic structures. And then we would witness the grand finale, the moment the first stars and quasars ignited. Their intense ultraviolet radiation would have acted like a cosmic blowtorch, striking the surrounding hydrogen fog and violently stripping electrons from their atoms. This process, called reionization, would have burned bubbles of clarity into the opaque neutral gas. In our 21-centimeter movie, these growing bubbles would appear as voids, as silent spots where the hydrogen's steady hum suddenly goes quiet. We would see these bubbles of ionized plasma grow and merge, until eventually the entire cosmic fog was burned away, ending the Dark Ages and making the universe transparent to light as we know it today. This signal is the ultimate record of the dawn, a direct broadcast from the era of first light. Yet that steady radio hum from the hydrogen fog might have been joined by a far stranger kind of light. What if the very first stars were not stars at all in the way we understand them? This brings us to a theory so radical it reimagines the dawn of light itself. The possibility of dark stars. Imagine an object that looks like a star, that glows with immense power, but whose heart beats to a completely different rhythm. A dark star would not be powered by the nuclear fusion that fuels our sun. Instead, its immense energy would come from the annihilation of dark matter. According to this idea, the first dark matter halos would have been incredibly dense, packed with these mysterious particles. As normal hydrogen gas fell into these halos, it would have dragged a huge amount of dark matter along with it, concentrating it at the center. If certain types of dark matter particles are their own antimatter opposites, Then when they collide, they would annihilate each other, converting their mass directly into pure energy. This process would generate immense heat and light from within the core of the collapsing gas cloud. This dark matter annihilation energy would be incredibly efficient. It would create an outward pressure so powerful that it could halt the gravitational collapse of the gas cloud, preventing it from ever becoming dense and hot enough to ignite nuclear fusion. The object would stabilize, shining brightly as a dark star. These entities would have been almost unimaginably vast. A single dark star could grow to be millions of times more massive than our Sun and shine with a steady, warm glow for millions of years. Their light would be softer and more diffuse than the violent ultraviolet radiation from the first fusion-powered stars. If dark stars did exist, they would have completely rewritten the early cosmic narrative. They would have lit up the universe long before traditional stars could form, pushing back the timeline of first light by many millions of years. This earlier, gentler dawn would have begun the process of reionization much more slowly, subtly altering the way the cosmic fog was burned away. The hunt is now on for these ghostly giants. Astronomers are searching the deepest images of the universe, looking for objects that are too red, too large, and too dim to be explained by any conventional star or galaxy. Finding just one would be a discovery of monumental proportions, proving that the darkness was broken not by a familiar fire, but by something entirely new and profoundly strange. While dark stars are a speculative possibility, another kind of seed may have been hiding in the primordial fog, one born from the universe's most violent first moments. Primordial black holes are a theoretical concept, tiny singularities that could have formed from the intense density fluctuations in the very first second after the Big Bang. Unlike the stellar black holes we know today, which are the corpses of massive stars, these would have been forged in the cosmic fireball itself. Their sizes could range from as small as an asteroid to as massive as a planet, all compressed into a microscopic point. If they existed in sufficient numbers, these black holes would have been the ultimate dark matter. They would have been scattered everywhere throughout the Dark Ages, invisible yet possessing immense gravitational pull. Each one would have acted as a perfect gravitational anchor. As clouds of neutral hydrogen drifted through the darkness, they would have been irresistibly drawn toward these tiny, dense points. A single primordial black hole, even a small one, would have created a powerful gravity well in its immediate vicinity, a pit that passing gas could not escape. This would have jump-started the process of star formation on a local scale. Instead of waiting for vast dark matter halos to slowly pull gas together over hundreds of millions of years, small pockets of gas could have collapsed much faster around these black hole seeds. This theory suggests the first stars and small galaxies could have ignited significantly earlier than our standard models predict, punching holes in the darkness long before anyone expected. But their role may not have been limited to just gravity. The smallest of these primordial black holes, those with the mass of a mountain or less, would have had a fascinating and explosive end. According to Stephen Hawking's famous theory, black holes are not completely black. They slowly radiate away their mass, a process known as Hawking radiation. For a supermassive black hole, this evaporation is negligible over the age of the universe. But for a tiny, asteroid-mass primordial black hole, the story is very different. Its small size makes it incredibly hot, and it would radiate energy at a phenomenal rate. After billions of years, it would eventually explode in a final, violent burst of particles and radiation. Now consider this happening during the Dark Ages. A population of these tiny black holes reaching the end of their lives simultaneously would have flooded the cosmos with high-energy radiation. This could have provided a widespread alternative energy source for reionization. It would have been a cosmic fireworks show of pure vacuum decay, blasting the electrons off hydrogen atoms and helping to clear the fog, not with starlight, but with the death cries of the universe's most ancient and fundamental objects. The hunt for evidence of these primordial seeds is ongoing. Their unique gravitational signatures could subtly alter the patterns we see in the cosmic microwave background, or they might be detected by their lensing effects on distant starlight. Finding them would mean that the universe's darkest age was not just a quiet prelude, but was instead punctuated by the silent, gravitational hum of countless tiny monsters, each one a relic from the first instant of time, secretly shaping the dawn. Our own galactic neighborhood holds a ghost story written in the emptiness of space. The Milky Way is not alone. Our standard cosmological models predict it should be surrounded by a vast entourage of thousands of small dwarf galaxies, ancient relics that formed during the cosmic dark ages. These tiny, faint galaxies are the leftover building blocks from the era of first light, the primordial fossils that should still be orbiting us today. Yet when astronomers look, they find only a few dozen. This is the mystery of the missing satellites, a glaring discrepancy between our theoretical predictions and the observed reality of the local universe. It is as if we have found the grand cathedral of our galaxy, but all the cobblestones that should pave the surrounding square have simply vanished. This is not a small error in our calculations. It is a fundamental challenge to our understanding of how the first small-scale structures coalesced from the dark. One compelling theory suggests that the first starlight itself was the culprit. When the earliest massive stars finally ignited, they did not just glow, they screamed. They flooded the cosmos with an incredibly intense blast of ultraviolet radiation. This cosmic flood would have swept through the universe, targeting the smallest, most vulnerable dark matter halos. Inside these tiny halos, the radiation would have struck the nascent clouds of hydrogen gas, heating them violently and stripping them away before they could ever collapse to form stars. The gravitational skeletons, the dark matter halos, would still be there today, invisible and dark, but they would be sterile, robbed of their gaseous fuel. We would not see them because they never lit up. They are galactic ghosts present in our gravitational maps but absent from our telescopes. Another possibility pushes the mystery even deeper, questioning the fundamental nature of dark matter itself. What if it is not completely dark and collisionless? What if dark matter particles can interact with each other through some unknown force, a kind of dark light or dark electromagnetism? This self-interacting dark matter would behave more like a fluid than an invisible, non-interacting gas. In small halos, this interaction would generate a subtle pressure, preventing the dark matter from clumping as densely as in our standard models. A less dense halo would mean a weaker gravitational pull, making it even harder to capture and hold onto the gas needed to form stars. This would naturally erase a vast population of the smallest, faintest galaxies from the visible sky, solving the missing satellites problem by changing the very rules of the invisible architecture. The silence in our galactic backyard is not empty. It is filled with questions. Are we surrounded by a vast, dark population of failed galaxies, or is the invisible stuff of the universe far more complex and dynamic than we ever imagined? Gravity was not the only sculptor at work in the primordial dark. A far more subtle force may have been weaving invisible threads through the cosmic fog, guiding its movements in ways we are only beginning to understand. This is the theory of primordial magnetic fields. The question is not just whether they existed, but how such a delicate influence could possibly leave a mark on an era dominated by immense gravitational pull. According to some models, these magnetic fields were not born in stars or galaxies. They were generated in the universe's first frantic moments, perhaps by the violent churning of the primordial plasma or by phase transitions as fundamental forces split from one another. These would have been incredibly weak seed fields, billions of times fainter than the magnetic field that holds a fridge magnet to your door. In the modern universe, such a whisper would be utterly insignificant. But in the near-perfect vacuum of the Dark Ages, where the only competition was the slow, patient pull of gravity, even the faintest magnetic field could become a guiding hand. Picture a vast, featureless cloud of hydrogen gas beginning to feel the tug of a dark matter halo. Without magnetic fields, the collapse is a simple, chaotic inward rush. But introduce even a trace magnetic field and the physics changes. The field lines, like countless invisible rails, would become trapped within the collapsing gas. As the cloud condensed, these lines would be squeezed together, strengthening the field locally. This newly intensified magnetism would then push back. It would provide a form of pressure, a subtle resistance that could slow the collapse of the gas, particularly in directions perpendicular to the field lines. This could prevent a cloud from fragmenting into as many small clumps, potentially leading to the formation of fewer but more massive first stars. The fields would also channel the flow of material, guiding ionized gas along these cosmic highways and influencing the rotation of the earliest structures. Their presence would have added a layer of delicate complexity to the brute force work of gravity, potentially leaving a distinct fingerprint on the properties of the very first stars and the shape of the earliest galaxies. The hunt for evidence of these primordial fields is a search for this ghostly signature. Astronomers look for the faint polarization of light from the cosmic microwave background, or for unusual patterns in the radio waves from the most distant hydrogen. Finding it would mean that the darkness was not just a canvas for gravity, but was also threaded with an invisible, ordered structure from the very beginning, a cosmic blueprint written in lines of force. These first stars were cosmic titans built from a universe of pure potential. They were the original generation, what astronomers call population 3 stars. Unlike every star that came after, including our own sun, these pioneers were made from only the two simplest ingredients the Big Bang provided: pristine hydrogen and primordial helium. There were no heavier elements, no carbon, no oxygen, no iron, nothing that astronomers collectively call metals. This purity had a profound consequence. Without metals, the gas clouds that collapsed to form these stars could not cool down efficiently. In later star formation, dust grains and heavy elements act like a cosmic coolant, radiating away heat and allowing a cloud to fragment into many smaller clumps. But for population 3 stars, this cooling mechanism did not exist. The gas remained hot and resisted fragmentation, leading to a runaway collapse that created behemoths. A single one of these first stars could have been hundreds of times more massive than our Sun. Imagine a star so vast it could contain our entire solar system within its diameter, a searing ball of hydrogen fusing at a ferocious, unsustainable rate. Their surfaces would have been scorchingly hot, blazing with a brilliant blue-white light and pouring out torrents of lethal ultraviolet radiation. Their lives were not long, epic sagas, but short, violent bursts of cosmic brilliance. A star like our Sun will burn steadily for billions of years. A massive population 3 star would have lived fast and died young, exhausting its nuclear fuel in just a few million years. Their deaths were as monumental as their births. When their cores ran out of fuel, they would have collapsed under their own immense weight and then exploded in supernova of unimaginable power. These were not ordinary supernovae. Some may have been so violent that they completely obliterated themselves, leaving no black hole or neutron star behind, just an expanding cloud of stellar debris. And within that debris was the ultimate legacy of the population 3 stars, the first complex chemistry of the cosmos. The incredible heat and pressure of their explosions forged the universe's first heavy elements. Every atom of carbon in your body, every breath of oxygen you take, every piece of iron in your blood was originally forged in the heart of a massive star and then blasted into the void by a supernova. These first supernovae were the universe's first alchemists, transforming the simple primordial soup into a rich, complex broth. They polluted the pristine gas clouds from which the next generation of stars would form. This pollution was the key to everything that followed. It allowed later stars to form with a mix of elements to be smaller, cooler, and longer lived. It allowed the formation of rocky planets. It made the chemistry of life possible. So the death of these first titans was not an end. It was the necessary sacrifice that seeded the cosmos with the raw materials for planets, for life, and for us. The Dark Ages did not end with a gentle sunrise. It ended with the explosive death cries of the universe's first giants, a spectacular firestorm that lit the fuse for the cosmic story we are a part of today. The echoes of that first cosmic firestorm were not entirely silenced by the ensuing dark. A fossilized vibration was left behind, a ghostly ruler etched into the very architecture of space. This is the theory of Baryon acoustic oscillations, a frozen sound wave from the universe's infancy that set the rhythm for everything that followed. In the first few 100,000 years, the cosmos was a searing, dense plasma, a soup of particles and light. In this hot medium, gravity was constantly trying to pull matter together into clumps. But it faced a powerful opponent, the intense pressure of radiation, which was trying to push everything apart. This created a tug of war, a cycle of collapse and rebound that sent powerful spherical pressure waves like sonic booms rippling outward through the primordial fire. Each wave traveled at a significant fraction of the speed of light, carrying a shell of compressed matter at its leading edge. Then, the universe cooled just enough for a pivotal event, the release of the cosmic microwave background. At that very moment, the music stopped. The plasma became a neutral gas, the radiation pressure vanished, and those racing pressure waves were instantly frozen in place. They left behind a vast, spherical imprint in the distribution of matter, a shell where an excess of hydrogen and helium had been gathered by the wave. This shell has a very specific size, a cosmic standard ruler determined by how far the sound wave could travel before the universe fell silent. During the long dark ages, this preferred scale was the dominant pattern in the cosmos. When dark matter began pulling the neutral gas into the first large-scale structures, it did not start from scratch. It worked with this pre-existing blueprint. The first clusters of matter naturally formed with a tendency to be separated by this specific distance, the radius of that ancient frozen sound wave. The incredible part is that we can still see this pattern today. When astronomers create three-dimensional maps of millions of galaxies in the modern universe, they do not see a random distribution. They find a subtle but statistically overwhelming preference for galaxies to be separated by a certain scale, a distance that has stretched with the expansion of the universe to nearly 500 million light-years. By measuring this fossilized ruler, scientists can perform extraordinary cosmic archaeology. They can trace the expansion history of the universe with incredible precision, revealing the tug of dark energy and the push of dark matter. This single, imprinted vibration from the first cosmic moments gives us a direct measurement of the conditions that prevailed throughout the Dark Ages, a fundamental chord that still resonates in the vast emptiness between the galaxies. Those first cosmic seeds, the tiny quantum ripples that grew into galaxies, did not appear by chance. Their origin story stretches back to a time so early it defies comprehension, to a theory known as cosmic inflation. This was not the gradual expansion we see today, but a violent, exponential growth spurt that occurred in the universe's first fleeting fraction of a second. In that incredible instant, a patch of space smaller than a single atom was stretched to a size larger than our entire observable universe. This process did more than just make the cosmos vast. It took the faint quantum jitters of the newborn universe, the tiny uncertainties inherent to empty space itself, and blew them up to cosmic proportions. These amplified jitters became the primordial density fluctuations, the subtle hills and valleys in the fabric of the cosmos. They were minuscule variations of less than 1 part in 100,000, but they were everything. In the profound uniformity of the Dark Ages, these fluctuations were the only game in town. They were the universe's sole source of variation, the only places where gravity had a slightly stronger grip. A region with just a tiny bit more density than its surroundings possessed a slightly stronger gravitational pull. Over the hundreds of millions of years of darkness, that small advantage compounded. It pulled in a little more dark matter, then a little more hydrogen gas. That initial speck of extra density, a fossil from the inflationary burst, became the core of a dark matter halo, which then became the birthplace of the first star. The grand cosmic web, the vast architecture of clusters and voids we see today, was entirely encoded in those initial microscopic imperfections. This theory creates a direct, unbroken chain from the quantum weirdness of the universe's first moment to the brilliant dawn that broke the long cosmic night. The light of the first stars was simply the long-delayed echo of inflation's final tremor. That invisible cosmic scaffolding might not be as rigid as we think. The theory of warm dark matter challenges the very nature of the universe's hidden architecture. We have been working under the assumption that dark matter is cold, meaning its particles are slow-moving and heavy, clumping together easily from the smallest scales upward. But what if dark matter is warm? This alternative proposes its particles are far lighter and faster, moving at a significant fraction of light speed in the early universe. This single change in property would have reshaped the entire dark ages. Particles moving at such high speeds would have been able to stream freely out of the smallest gravitational potholes, effectively washing away the tiniest density fluctuations. Think of it like trying to build a sandcastle with dry, fine sand. With cold, dark matter, the sand is wet and sticky, allowing you to form small, detailed structures immediately. With warm, dark matter, the sand is dry and loose. Any small mound you try to build simply flows apart. Only the largest, most massive gravitational potentials could have held onto these speedy particles. The consequence is profound. In a warm dark matter universe, the very first structures to form would not have been countless tiny halos. Instead, the cosmos would have remained almost perfectly smooth for longer, with the first significant clumps appearing later and on a much larger scale. The formation of the very first stars and proto-galaxies would have been delayed. There would have been no population of faint, early dwarf galaxies. This elegantly solves the missing satellites problem, not by making the small halos dark and sterile, but by preventing them from forming in the first place. The cosmic dawn would have arrived later, and when it did, it would have begun with a smaller number of larger, brighter beacons igniting across the void. This delayed and consolidated start would have sent a powerful ripple through cosmic history, fundamentally altering the timeline and pattern of reionization. The great cosmic fog would have been burned away by fewer, more intense sources, creating a different mosaic of ionized bubbles in the hydrogen haze. The hunt for warm dark matter is a hunt for this absence. Astronomers search the deepest reaches of space, looking for a telltale lack of the smallest, oldest galaxies. Finding that the early universe was devoid of these tiny building blocks would be compelling evidence that the dark side of the cosmos is not cold and sluggish, but warm and swift. While the universe slept, it may have been threaded with cosmic scars from its violent birth. Cosmic strings are theoretical fissures in space-time, one-dimensional cracks that could have formed as the fundamental forces of nature froze into their current state. Picture a vast block of ice forming, with intricate cracks and fissures appearing as it solidifies. Cosmic strings would be like that, but etched into the fabric of reality itself. These would not be strings of matter, but flaws in the cosmic order, unimaginably dense and thinner than a single atom, yet stretching across the entire observable universe. Their gravitational influence would have been immense, warping the space around them like a massive, invisible wire cutting through the darkness. During the Dark Ages, as the neutral hydrogen fog drifted, it would have felt this profound pull. Any cloud of gas passing near a cosmic string would be irresistibly drawn into its gravitational wake. These strings would have acted as cosmic zippers, stitching together linear filaments of denser matter. Instead of matter clumping into spherical halos alone, These strings would have created straight, dense lines of hydrogen gas like beads on an invisible thread. This process would have provided a powerful shortcut for gravity. While dark matter halos were slowly pulling gas into potholes, cosmic strings could have been rapidly drawing matter into long, thin rivers. The first stars to ignite might not have been scattered randomly, but aligned in brilliant linear patterns, tracing the ghostly contours of these primordial defects. The entire cosmic web we see today, with its vast filaments of galaxies connecting at dense nodes, might bear the imprint of this early string network. The great walls and threads of galaxies could be the amplified echoes of these initial, razor-thin scars. The hunt for evidence of cosmic strings is a search for these anomalous patterns in the sky. Astronomers look for double images of distant quasars, split by the gravitational lensing of a string, or for strange, linear ripples in the cosmic microwave background. Finding one would be like discovering the original stitching that held the dark cosmos together, revealing that the universe's largest structures were guided into existence by the faintest of flaws from its first moment. But those first stars may have been outshone by monsters. The quasar-led reionization theory suggests the real heroes, or perhaps villains, of the cosmic dawn were not stellar titans, but the most violent engines in the universe. Quasars are the intensely bright hearts of distant galaxies, powered by a gluttonous supermassive black hole. As vast rivers of gas spiral into this gravitational abyss, the material doesn't just vanish. It forms a searing, swirling disk of doom, heated to millions of degrees by friction and magnetic fields before it crosses the point of no return. This process is incredibly wasteful in the most productive way possible, converting the mass of falling gas into a blistering torrent of high-energy radiation. This isn't the bright but relatively soft ultraviolet light of a massive star. This is a focused beam of hard ultraviolet and even X-ray radiation, a far more potent and penetrating form of energy. A single, brilliant quasar can outshine an entire galaxy of 1 billion stars. Its radiation isn't just a gentle glow, it's a cosmic blowtorch. When this intense beam struck the neutral hydrogen fog of the Dark Ages, it didn't just nudge electrons away from their atoms. It blasted them off with immense force. The theory proposes that these quasar beams were uniquely efficient at carving out vast, cleared bubbles in the opaque hydrogen. They could ionize hydrogen across immense distances, far beyond the local neighborhood of a star-forming region. This paints a very different picture of how the cosmic fog was lifted. Instead of a gentle, uniform dawn where starlight slowly brightened the cosmos, reionization becomes a more chaotic and patchy process. The universe would have looked like a strange, cosmic Swiss cheese. Isolated bubbles of crystal-clear, ionized plasma would have appeared around the earliest quasars, brilliant beacons in an otherwise dark sea. For millions of years, these cleared regions would have grown and expanded, only slowly beginning to overlap with bubbles created by other, less powerful sources. The end of the Dark Ages, in this view, was not a sunrise. It was a series of brilliant searchlights flickering on in a deep fog, each one violently burning a hole in the fabric of the night. The final transparency of the universe was not a gentle blanket being pulled back, but the merger of these violent, expanding spheres of influence. This theory shifts the timeline and the mechanism, suggesting that the most extreme objects in the cosmos may have played the dominant role in shaping the very medium through which we now see the stars. The nature of the invisible architect itself could have rewritten the cosmic timeline. Supersymmetry is one of the most elegant ideas in all of theoretical physics, a potential framework that would complete the standard model by giving every known particle a hidden superpartner. For the photon, there would be the photino, for the quark, the squark. This symmetrical universe is beautiful, but it also provides a perfect solution to one of our greatest mysteries. The lightest of these superpartners, a particle known as the neutralino, is stable, massive, and barely interacts with normal matter. It is, in other words, an ideal candidate for the dark matter that shaped the cosmos. If this theory is true, then the Dark Ages were not just sculpted by an inert gravitational substance. They were influenced by a dynamic, interactive one. The neutralino, crucially, is its own antiparticle. This means that when two neutralinos collide, they can annihilate each other in a flash of pure energy, converting their mass into radiation, gamma rays, and other particles. In the sparse voids of the modern universe, such events would be incredibly rare. But during the Dark Ages, within the first, incredibly dense dark matter halos, the conditions were perfect for a frenzy of annihilation. Imagine those primordial gravitational potholes not as silent traps, but as faintly glowing cauldrons of particle decay. This constant, low-level energy injection would have acted like a cosmic heating pad, subtly warming the hydrogen gas that was falling into the halos. A warmer gas is a puffier gas, more resistant to the crush of gravity. This single effect could have thrown a wrench into the delicate clockwork of the first star formation. In some scenarios, this heat could have significantly delayed the collapse of gas clouds, pushing back the moment of ignition by millions of years. The cosmic dawn would have been postponed, the universe lingering in its dark, neutral state for longer than our standard models predict. Yet in other models, the story flips. The same annihilation products, electrons and photons, could have provided the very catalysts needed for the gas to cool and collapse faster. By helping the gas shed its energy, this process might have actually accelerated the birth of the first stars, making the dawn break earlier and more abruptly. The legacy of supersymmetric dark matter would be a subtle but profound fingerprint on the entire reionization process, altering the rhythm and the chorus of that first light. The search for this signature is a double hunt. Particle physicists are using colossal underground detectors, hoping to feel the faint bump of a neutralino. Meanwhile, cosmologists are refining their models of the early universe, looking for any telltale sign in the ancient hydrogen signal or the pattern of the first galaxies that points to a dark matter that was not just cold but alive with hidden interactions. That first great clearing of the cosmic fog was not a gentle, uniform sunrise. The end of the Dark Ages was a messy, chaotic affair, a patchwork of light and shadow. This is the theory of lumpy reionization. It suggests the universe did not become transparent all at once, but rather in a series of isolated, growing bubbles. Imagine a vast, dark ocean on a moonless night. Suddenly, a single, brilliant lighthouse flickers on in the distance. Its powerful beam does not illuminate the entire sea, but it carves out a massive sphere of clarity around itself, a bubble of light in the endless dark. That is how reionization began. The brightest sources, whether clusters of massive population, 3 stars, or the violent beams of early quasars, acted as those first lighthouses. Their intense radiation blasted the electrons from the surrounding hydrogen atoms, creating localized spheres of ionized, transparent plasma. For millions of years, the universe was a cosmic Swiss cheese, a strange amalgamation of these brilliant, cleared voids and the vast, lingering neutral fog in between. This was a deeply uneven process. A pocket of space fortunate enough to be near a brilliant quasar would have been flooded with light millions of years before a more isolated region, still waiting in the dark, felt the faint glow from a smaller group of stars. Some parts of the cosmos remained stubbornly dark, trapped in the cosmic equivalent of a deep shadow, long after their neighbors had been bathed in the light of the first dawn. This lumpiness is not just a detail. It is a direct record of the first generation of light sources. The size, distribution, and growth rate of these ionized bubbles are a frozen echo of the power and population of the stars and quasars that created them. A universe where reionization was driven by many small, scattered stars would have produced a fine, frothy pattern of small bubbles that merged slowly. A universe dominated by a few monstrous quasars, however, would have been characterized by a handful of enormous, rapidly expanding voids, By trying to map this ancient patchwork, astronomers are essentially conducting a cosmic census of the first luminous objects. They are searching for the subtle imprint of this lumpiness in the faint whispers of the 21-centimeter line from hydrogen, or in the way the light from the most distant quasars is filtered through the final remnants of the fog. Reading this lumpy history is our best chance to understand what finally broke the long silence, and whether it was a chorus of countless stellar voices or the solitary shout of a few cosmic giants that truly ended the night. That primordial gas was anything but a placid, sleeping sea. It was a cosmic fluid churning with unseen energies that dictated the rhythm of the first star formation. This is the theory of turbulence in the primordial gas, a hidden force of chaos that could have either braced the clouds against gravity's pull or brutally crushed them into new stars. Turbulence is the wild, disordered motion within a fluid, the same kind of swirling, chaotic energy you see in a rapidly flowing river or a billowing storm cloud. In the modern universe, it is often driven by supernova explosions or by the violent collisions of galaxies. But in the pristine dark ages, what could possibly have stirred the pot? The seeds for this primordial turbulence may have been planted by the same colossal sound waves that created the Baryan acoustic oscillations, their residual ripples setting the gas into a slow cosmic simmer. Later, as the first titanic stars lived and died, their cataclysmic supernova would have acted like colossal spoons, violently stirring the cosmic soup and injecting a new, more powerful form of turbulence. This invisible churning had a profound and dual nature. On one hand, turbulent motion creates a kind of internal pressure, a persistent jostling that can hold a vast cloud of gas apart, effectively propping it up against its own weight. In this scenario, turbulence acts as a regulator, a cosmic force of restraint that slows down the process of gravitational collapse. It could have stretched out the timeline of the first star formation, forcing the gas to clump together more gradually over many millions of years. Yet, in a stunning contradiction, turbulence can also be the ultimate trigger. When two powerful turbulent streams collide, they create immense shock waves, regions of sudden, extreme pressure. These shocks act like cosmic hammers, slamming into pockets of gas and compressing them to densities far beyond what gravity could achieve alone. In the darkness, these turbulent collisions would have created the perfect, high-density seeds for the rapid birth of stars. So, the Dark Ages were not a time of simple, quiet gathering. They were a dynamic and messy arena where the chaotic dance of turbulence constantly battled the steady, patient pull of gravity. The efficiency of the very first star formation, and therefore the timing of the cosmic dawn itself, may have hinged on this invisible, chaotic weather moving through the silent, waiting fog. That silent cosmic assembly line was not a gentle process. The first small proto-galaxies did not simply grow in peaceful isolation. They engaged in a brutal, hierarchical dance of mergers and cannibalization. These violent collisions were a primary engine for cosmic evolution during the latter part of the Dark Ages. Picture two of these early, fuzzy collections of stars and gas, each held together by its own dark matter halo, drawn together by their mutual gravitational pull. They would not simply bump and stick. Their collision would have been a chaotic, cosmic car crash, sending immense shock waves rippling through their constituent gas. This violence, however, was profoundly creative. The chaotic interactions would have robbed the gas clouds of their orbital energy, funneling vast rivers of hydrogen directly toward the center of the new, merged galaxy. This sudden, catastrophic inflow of fuel would have triggered ferocious bursts of star formation, far more intense than anything possible in a quiet, isolated cloud. It was a stellar baby boom on a cosmic scale, lighting up the darkness with a firestorm of new suns, but the consequences went even deeper. This same funneling of gas would have also fed the monstrous seeds lurking in the galactic cores, the early black holes. A sudden feast of fresh material would have caused these black holes to balloon in size at a staggering rate, potentially igniting them into the brilliant quasars that acted as cosmic blowtorches. This merger-driven evolution solved a critical puzzle. How did the universe build giant galaxies and supermassive black holes so quickly after the dawn of first light? The answer was cannibalism. Through a relentless series of collisions and acquisitions, small structures rapidly assembled into larger, more complex ones. This process did not just build bigger galaxies, it built different kinds of galaxies, seeding the diversity of spiral and elliptical shapes we observe in the modern universe. The end of the Dark Ages, therefore, was not just illuminated by the gentle glow of the first stars. It was also punctuated by the brilliant, violent flashes of galactic collisions, a cacophony of mergers that simultaneously built the cosmic landscape and helped burn away the final remnants of the primordial fog. The very nature of the invisible cosmic architect might be far stranger than we have dared to suppose. Another compelling theory suggests dark matter is not made of heavy, sluggish particles, but of something almost ethereal. This is the action dark matter hypothesis. Actions are hypothetical particles born from theories attempting to solve deep puzzles in particle physics, and they are unimaginably light. A single action would be billions of times less massive than even an electron. But if they exist in truly staggering numbers, they could collectively account for all the dark matter in the universe. This lightness comes with a profound consequence. Due to the quantum rules that govern the very small, these featherweight particles would not behave like tiny billiard balls. On the scale of a small galaxy, they would act more like a wave, a coherent, rippling field of energy permeating all of space. This concept is known as fuzzy dark matter. Imagine the difference between a hailstorm and a dense, uniform fog. The hailstorm, with its individual, heavy pellets, is like cold, dark matter, easily forming small, sharp clumps. The fog, however, is a wave-like entity that resists being compressed into tiny droplets. It naturally smooths itself out on small scales. An action fog filling the Dark Ages would have done exactly that. It would have suppressed the formation of the very smallest cosmic structures. Those tiny, faint dwarf galaxies that are missing from our local universe would never have had a chance to form, not because their gas was stripped away, but because the fuzzy dark matter refused to clump on such a small scale to begin with. This offers an elegant solution to cosmology's small-scale problems. The first structures to emerge in an action-dominated cosmos would have been inherently larger, shifting the entire timeline and pattern of the first star formation. The grand cosmic dawn would have begun with fewer, more substantial beacons igniting across the void. This unique history would have left a clear fingerprint, a specific pattern of fluctuations in the faint 21-centimeter radio hum from the primordial hydrogen. Our upcoming telescopes are searching for this exact signature. Finding it would not only reveal the identity of dark matter, but would force us to rewrite the story of the Dark Ages, painting a picture where the universe's foundation was not a scaffold of heavy particles, but a rippling quantum sea of unimaginable lightness. The death of the first stars was a creative apocalypse. When those primordial titans, the population 3 stars, reached the end of their brief lives, they did not fade quietly. Their cores collapsed and they erupted in supernova explosions of such staggering power that they could outshine an entire modern galaxy. This was the universe's first great act of cosmic recycling. In the heart of those stellar infernos, for the first time ever, atomic nuclei were fused together into elements heavier than helium. Carbon, oxygen, nitrogen, and iron were forged in a single, violent instant, and then blasted out into the void at nearly the speed of light. This was the moment the periodic table was born, seeding the once pristine cosmos with the raw materials for future planets, oceans, and life itself. But the impact of these first supernova went far beyond mere chemistry. The explosion itself was a physical event of unimaginable force. The blast wave, a spherical shock front of energy and stellar debris, plowed into the surrounding clouds of cold, neutral hydrogen gas like a cosmic tsunami. This wave did two seemingly contradictory things. First, it acted as a cosmic sculptor. As it expanded, it swept up vast quantities of gas, piling it into incredibly dense, cool shells on its leading edge. Inside these compressed walls of hydrogen, the conditions became perfect for a new generation of star formation. The very violence of the death had created fertile nurseries, triggering a second wave of stellar births that were fundamentally different from the first. These new stars formed from gas that was already enriched with those first heavy elements, allowing them to be smaller, cooler, and longer-lived. Yet, for the smallest, most vulnerable structures in the cosmos, the supernova blast was an agent of destruction. For tiny protogalaxies dwelling in faint dark matter halos, the incoming wave of energy was catastrophic. The intense heat and radiation pressure simply blew the gas away, stripping these small halos of their star-forming fuel entirely. They were left as dark, sterile ghosts, unable to ever light up. This feedback loop, where the death of one generation of stars dictates the birth of the next, became a fundamental regulator of cosmic evolution. It meant the universe could not light up all at once. The first starlight actually slowed down the spread of subsequent starlight, ensuring the dawn emerged in a controlled, rhythmic fashion, one supernova-triggered burst at a time. Those supermassive black holes anchoring modern galaxies present a profound timing problem. How could they grow to billions of solar masses so quickly after the first stars were born? The direct collapse black hole theory offers a daring solution, one that bypasses stars entirely. Imagine a vast, pristine cloud of hydrogen gas in the early darkness, drawn into one of the first massive dark matter halos. In most scenarios, such a cloud would fragment as it collapses, shattering into hundreds of individual stars. But for a direct collapse, the conditions must be perfect and strangely hostile. The gas must be kept so hot that it cannot cool down and break apart. This requires an environment utterly devoid of the one thing that normally aids cooling heavy elements. It also needs a powerful external source of heat, a constant bath of ultraviolet radiation from a nearby, already forming galaxy. This radiation batters the gas cloud, keeping its atoms excited and preventing them from shedding energy. Trapped in this hot, monolithic state, the entire cloud has only one path left. It collapses as a single, coherent unit. There is no fragmentation, no glittering burst of stellar birth. Just a silent, catastrophic implosion. The center of the cloud becomes so dense that a gravitational point of no return forms, not from a dead star, but from the raw primordial gas itself. In one swift cosmic event, a black hole is born with a starting weight of tens of thousands, even hundreds of thousands of solar masses. This is not a stellar corpse, it is a primordial titan, a seed of unprecedented size planted directly into the cosmic soil. These dark seeds would have been the ultimate cheat code for the early universe. While smaller black holes from dead stars would have to slowly and painstakingly grow by accreting gas, these direct collapse monsters started life as giants. They were perfectly positioned to gorge on the abundant gas surrounding them, ballooning at a prodigious rate to become the supermassive black holes that power the brilliant quasars we see just a few 100 million years later. They were not the products of the cosmic dawn, but its hidden architects lurking in the deepest dark and waiting for their moment to violently reshape the newborn cosmos. The silent cosmos of the Dark Ages may have been stirred by ghosts. Among the most abundant particles in the universe are neutrinos, ethereal phantoms that barely interact with matter. The standard model of particle physics describes them, but it leaves many questions unanswered. The Neutrino Minimal Standard Model, or new MSM, proposes an elegant extension. It adds just 3 new, heavier types of neutrinos to the cosmic family. This simple addition could have quietly reshaped the entire dark era. One of these heavy neutrinos is theorized to be stable. It would not decay, and its significant mass could make it a perfect candidate for the dark matter that sculpted the first cosmic structures. The other two heavy neutrinos, however, would have been unstable. Living only for a fleeting moment after the Big Bang, their brief lives and dramatic decays would have been a source of significant energy. This energy injection could have acted like a faint, universal heater, subtly warming the primordial soup of hydrogen and helium gas. Even a tiny amount of extra heat would have had profound consequences. A warmer gas is more energetic and puffy, more resistant to the relentless crush of gravity. This could have slightly delayed the collapse of the first gas clouds, postponing the moment the first stars ignited and extending the long cosmic night by a critical few million years. Alternatively, the decays of these particles could have influenced the delicate balance of light elements, leaving a faint chemical fingerprint on the primordial gas that later changed how efficiently it could cool and collapse. The universe that emerged from this subtle neutrino influence would have been slightly different, its initial conditions for star formation tuned by the invisible hand of these heavy, fleeting phantoms. This theory reminds us that the darkness was not a perfect vacuum, but a dynamic arena where even the most elusive particles could have left their mark on the dawn. That steady cooling of the primordial gas might have been far more efficient than we ever guessed. Most models paint the Dark Ages as a long, slow chill, a gradual descent into cold that finally allowed gravity to take hold. But what if the cosmos discovered a shortcut? The theory of a cool dark age proposes that unknown physical processes supercharge the cooling of that hydrogen fog, allowing the first stars to ignite in a sudden, brilliant flash. In the standard story, the main way the gas could cool was through the faint emission of radiation as hydrogen atoms paired up into simple molecules. It was a slow, inefficient process, but perhaps dark matter itself was the secret coolant. If certain types of dark matter particles can interact with normal protons and electrons, even very weakly, those collisions could have siphoned thermal energy away from the gas. Picture the dark matter as a vast, invisible heat sink, drawing the warmth out of the hydrogen fog and radiating it away into the void. Another possibility involves more complex chemistry in the darkness. Trace amounts of lithium hydride, one of the first molecules to possibly form, could have been a remarkably effective coolant, its rotations and vibrations emitting infrared light and bleeding energy away from the gas clouds with surprising speed. The consequence of such enhanced cooling would have been dramatic. Colder gas is softer, more pliable. It loses its internal pressure and resistance far more quickly. When a cold cloud of gas falls into a dark matter halo, it doesn't just slowly condense, it crumbles. It fragments rapidly and violently into a multitude of dense clumps, each one a potential stellar nursery. In this scenario, star formation is not a slow, stately process. It is an epidemic. The first stars would not have been isolated titans igniting here and there across a vast, dark emptiness. They would have burst forth in dense, brilliant clusters, lighting up the cosmos in a sudden, coordinated blaze. The end of the Dark Ages would not have been a gradual sunrise, but a universe-wide flick of a switch. This accelerated dawn would have sent a powerful shockwave through cosmic history. Reionization would have begun earlier and progressed with breathtaking speed. The growing bubbles of ionized plasma around these countless early stars would have merged into a brilliant, transparent blanket in a cosmic instant, ruthlessly burning away the primordial fog. The entire timeline of cosmic structure formation would be compressed, forcing us to reconsider how quickly galaxies could assemble after first light. The evidence for this theory lies in the very first glimmers we can detect. If our most powerful telescopes begin to find that small, fully formed galaxies were already shining much earlier than our standard models allow, it would be a strong hint that the long cosmic night was cut short by a deep, unexpected chill. That subtle cosmic barcode from the primordial fog might not be telling the whole story. The statistical blueprint for the entire universe, the pattern of those first tiny ripples, could have been fundamentally different from what we assume. The standard model of inflation predicts that these initial density fluctuations were Gaussian. This is a specific statistical term meaning the fluctuations were random but followed a predictable bell curve-like distribution. Most regions were average, a few were slightly dense, and a few were slightly empty. It was a cosmic roll of the dice where extreme outcomes were incredibly rare. But what if the dice were loaded? Some alternative theories of inflation suggest they were, producing tiny but significant deviations known as primordial non-Gaussianity. In this scenario, the statistical rules were subtly skewed. Over dense regions, the hills that would become galaxies were not as rare as they should have been. The universe's initial conditions would have featured more of these dense peaks, and some of them would have been far more extreme than a standard Gaussian roll would ever allow. This statistical quirk would have sent a powerful ripple through the entire Dark Ages. Gravity would have found more places to get a strong, early grip. Those exceptionally dense peaks would have collapsed with breathtaking speed, becoming gravitational anchors much earlier in the cosmic timeline. The result would not have been a slow, steady awakening of lights across the void. Instead, the first stars and proto-galaxies would have ignited earlier, and crucially, they would have formed in tight, clustered groups. The cosmic dawn would have looked less like a sparse scattering of campfires in a vast dark plain, and more like brilliant cities flaring to life, with vast, empty deserts stretching between them. This clustered, accelerated start would have left a distinct fossil record in the sky. The pattern of the very oldest galaxies we can observe would not be random. They would show a clear preference for certain preferred distances from one another, a statistical signature of that initial skew. The great cosmic web would have been woven with a thicker, more clumped thread from the very beginning. Hunting for this signature is like looking for the ghost of a loaded die in the first moments of time. By meticulously mapping the distribution of the most distant galaxies and quasars, astronomers are searching for this telltale clustering, a faint echo that would force us to rewrite the rules of the universe's violent birth and reveal that the seeds of everything were not perfectly random, but slightly, mysteriously biased toward creating us. Our newest window on the cosmos is already shattering old panes of glass. The James Webb Space Telescope, humanity's most powerful time machine, is now gazing directly into the final moments of the cosmic dark ages. Its mission is to test every single theory we have discussed, and its first glimpses are delivering stunning surprises. Instead of finding a universe populated only by faint, infant blobs of stars, Webb is discovering galaxies that are shockingly bright, incredibly massive, and already displaying mature shapes like disks and spiral arms. These cosmic toddlers, seen when the universe was less than 500 million years old, appear to have grown up far too fast. They are cosmic prodigies, challenging the very timeline we thought we understood. How could such colossal structures assemble from the primordial darkness so quickly? This new data suggests that the processes of star formation and galaxy assembly were not slow and stately, but breathtakingly efficient. Perhaps the first stars formed in a sudden, coordinated burst, or maybe the invisible hand of dark matter was even more effective at gathering gas than our best models predicted. Each of these unexpectedly bright galaxies is a clue, forcing a profound re-evaluation of that long, dark era. The darkness may not have been a slow, patient prelude, but a frenetic, hidden construction zone, building the foundations of the cosmic web with a speed and skill we are only now beginning to witness. Our own universe's journey from darkness to light appears perfectly calibrated, but what if the dials of reality were set differently? This is the theory of the multiverse and its varying constants, a mind-bending idea that places our cosmic history within an infinite tapestry of possibilities. The fundamental forces and particle masses we take for granted, like the strength of gravity or the ratio of a proton's mass to an electron's, might not be universal truths. They could be local bylaws, random outcomes from the chaotic birth of our particular cosmic bubble. In another universe, just a fingertip away in a higher dimension, these constants could have entirely different values, and the dark ages would have unfolded in ways we can scarcely imagine. If the gravitational constant were slightly stronger, the patient pull of dark matter would have been a violent, crushing grip. The first dark matter halos would have formed with breathtaking speed, pulling the primordial hydrogen gas together in a frantic rush. The slow, billion-year gathering would have been compressed into a mere few 100 million years. The dark ages would have been a brief, dark whisper, ending in an abrupt, brilliant flash of countless stars igniting almost simultaneously. Conversely, a slightly weaker electromagnetic force would have been a cosmic catastrophe. This force is what binds electrons to atomic nuclei, allowing stable atoms like hydrogen to exist. If it were just a little weaker, atoms could not hold together. The universe would never have cooled into a stable neutral fog. There would have been no dark ages at all, because there would have been no dark, neutral universe to inhabit. It would have remained an eternal, searing plasma, a formless glow without structure or story. Our universe seems to have found a perfect, narrow ledge to walk. The constants are tuned with such precision that gravity was strong enough to build a cosmic web, but not so strong that it collapsed the universe immediately. The electromagnetic force was potent enough to forge stable atoms, creating the dark fog that was necessary for stars to eventually ignite within it. This delicate balance allowed for a long, quiet dark ages, a crucial incubation period where the first structures could slowly, steadily coalesce without being torn apart. While we may never be able to peer into another universe to test this idea, its power lies in the perspective it offers. It frames our entire cosmic dawn not as an inevitable outcome, but as a single, fortunate roll of the dice in a game with nearly infinite losing combinations. The long silence that gave birth to us was not a simple prelude. It was a fragile, fleeting moment in a much wider cosmic landscape, a quiet night that, in most other realities, never ended or never even began. That silent heating of the primordial fog could have come from a ghost within a ghost. Sterile neutrinos are a hypothetical and deeply strange particle, a phantom that would be even more elusive than the ordinary neutrinos that already barely interact with matter. Think of them as the ultimate introverts of the cosmos. While regular neutrinos will occasionally bump into another particle through the weak nuclear force, sterile neutrinos would refuse even that. Their only method of communication with the rest of the universe would be through the gentle tug of gravity. This makes them a perfect, if exotic, candidate for the dark matter that shaped the cosmos. But these phantoms might not have been completely stable. Some theories suggest that a sterile neutrino could be its own antiparticle, leading to a slow, inevitable process of decay. Over immense timescales, two sterile neutrinos could annihilate each other, and in that quiet disappearance, they would release a faint pulse of energy, often in the form of an X-ray photon. Now picture this process unfolding during the Dark Ages. The universe is filled with these sterile neutrinos, the unseen scaffolding of everything, and all across that vast, dark space, a constant, faint drizzle of X-rays is falling from their slow decay. This is not a violent blast of energy, but a pervasive, gentle rain. Each X-ray photon, when it strikes an atom in the hydrogen fog, would deposit a tiny amount of heat. Collectively, this drizzle would have acted as a cosmic space heater, subtly but persistently warming the gas. A warmer gas is more energetic and puffy. It resists collapse, so while gravity was patiently trying to pull the hydrogen into dense clumps within the dark matter halos, this background X-ray heating was pushing back, providing a low-level pressure that kept the gas from cooling down as efficiently. This single, subtle effect could have acted as a cosmic delay switch. The formation of the very first stars, which relies on cold, dense gas, would have been postponed. The cosmic dawn might have been pushed back by millions of years. the universe lingering in its dark, neutral state for just a little bit longer as this phantom rain gently warmed the cradle of creation. The evidence for this theory is written in that faint radio hum we discussed earlier, the 21-centimeter signal from the primordial hydrogen. The specific way the gas was heated would leave a unique fingerprint on the pattern of that signal. If our future telescopes can detect a subtle warmth in the ancient hydrogen that cannot be explained by stars or quasars, it may be the final, fading signature of these ghostly particles decaying in the dark, a whisper proving that the greatest structures were shaped by the most silent of decays. The silent expansion of the cosmos might have been driven by a phantom force. Dark radiation is a theoretical concept, a hypothetical form of energy carried by exotic, ultra-fast particles that are completely invisible to light and normal matter. Think of them as the ultimate ghosts, streaming through the early universe at nearly the speed of light without leaving a single scratch on the atoms of hydrogen or the photons of the cosmic microwave background. Their influence, however, would have been profound. In the Standard Model, the early universe's expansion was governed by the known forms of radiation and matter. Adding dark radiation to this mix is like turning up the heat under a simmering pot. These phantom particles would have increased the overall energy density of the cosmos, accelerating its expansion rate in those first critical moments. A faster expanding universe is a more diluted universe. The subtle hills and valleys in the density of matter, the seeds for all future structure, would have had less time to grow under gravity's pull. The great cosmic tug of war between gravity's inward pull and the universe's outward expansion would have been tilted, with expansion gaining a significant advantage. This single change would have rewritten the entire timeline of the Dark Ages. Key cosmic events would have been rescheduled. The moment the cosmic microwave background was released would have shifted. More importantly, the formation of the first dark matter halos, the gravitational anchors for starlight, would have been delayed. The universe would have remained smooth, dark, and neutral for a longer period, extending the long cosmic night by many millions of years. We can search for the ghost of this phantom force today by looking at the universe's fossilized blueprints. The Baryon acoustic oscillations, those frozen sound waves that act as a cosmic ruler, would have a different measured size if dark radiation had been present. The sound horizon, the specific distance those waves traveled before the cosmic microwave background was set, would be altered because the underlying music of the expanding cosmos would have played at a different tempo. Finding a discrepancy in this standard ruler would be like discovering that the foundational measurements of our reality were drawn on a subtly stretched canvas. The entire story of first light, from the patient gathering of gas to the brilliant flash of the first stars, would have unfolded against a different background to a different rhythm, all directed by particles we cannot see and may never directly detect. The darkness was threaded with countless miniature singularities. This theory pushes the primordial black hole idea to its ultimate conclusion, proposing that the invisible substance shaping our cosmos is not a sea of exotic particles, but a vast population of asteroid mass black holes, each a fossil from the universe's first instant. If true, the Dark Ages were not sculpted by a smooth, invisible fluid, but by a fine-grained cosmic gravel of unimaginable density. These tiny black holes would have been the ultimate dark matter, their collective gravity dominating the cosmos from the smallest scales upward. Their influence would have been immediate and profound. While particle-based dark matter must wait to clump into large halos, these primordial black holes were ready-made gravitational anchors from day one. Every slight overdensity in the primordial gas would have contained a swarm of these microscopic monsters, each one a potent seed for collapse. The first stars could have ignited in tiny, isolated pockets much earlier than our standard models predict, their formation triggered not by the slow accumulation of gas in a vast halo, but by the intense, localized pull of a single mountain mass black hole. This would have painted the dawn with a finer brush, creating a universe that lit up not with a few grand beacons, but with a delicate, widespread sparkle of early light. But their role was not purely gravitational. Each of these black holes, though small, would have been a dynamic engine. As they drifted through the primordial hydrogen fog, they would have acted like cosmic vacuum cleaners, steadily accreting wispy tendrils of gas. This slow, steady feeding would have generated friction and heat, causing each black hole to emit a faint, ghastly glow of X-rays. The collective radiance of trillions upon trillions of these feasting singularities would have produced a pervasive, low-level background radiation, a universal haze of soft X-rays bathing the entire Dark Ages universe. This phantom light would have provided a subtle, alternative source of energy, gently heating the hydrogen gas and potentially altering the delicate thermodynamics of the first star formation. And when two of these black holes crossed paths, drawn together by their mutual gravity, they would have spiraled inward and merged. Each collision would have been a tiny, violent tremor in space-time, sending out a ripple known as a gravitational wave. The cumulative effect of countless such mergers happening all across the cosmos during that long night would have generated a persistent hum, a stochastic background of gravitational waves that still echoes through the universe today. Our most sensitive detectors are now listening for this chorus, a fossilized vibration that would be the direct soundtrack of the Dark Ages, a symphony of collisions from a time when the universe was dark, silent, and filled with invisible, orbiting monsters. Yet all these theories of a singular dawn might be missing the grandest picture of all. Our universe's long, silent night may not have been a unique beginning, but merely one chapter in an endless cosmic story. This final theory proposes a cyclical universe where the cosmos experiences an eternal rhythm of birth, expansion, and rebirth. In one profound model known as conformal cyclic cosmology, the ultimate fate of our universe becomes the very seed for the next. As our cosmos expands into an unimaginably distant future, all matter is eventually consumed by black holes, which then slowly evaporate away through Hawking radiation. The universe becomes a cold, empty sea of pure, featureless radiation. In this state of maximum simplicity, the universe loses all sense of scale. A single photon traveling across this void experiences a reality with no distinct size or distance. At this point, the end of time for our universe can be mathematically identified with the beginning of time for a new one. The vast, silent emptiness becomes a new, hot, dense Big Bang. In this breathtaking view, the information from everything that ever existed in our universe, every galaxy, every star, every life, is not lost. It is imprinted onto the initial conditions of the next cosmic cycle, or eon. The subtle patterns we see in the cosmic microwave background, the faint echoes of the Dark Ages, might not be random quantum jitters. They could be the faded scars, the cosmic memories of a universe that lived and died before our own. The first dark matter halos that gathered in the darkness were not forming in a void, but were growing according to a blueprint written in a previous cosmic age. The first starlight that broke our Dark Ages was not the first light ever, but simply the latest dawn in an eternal cosmic rhythm. This transforms our entire understanding of that long silence. It was not a prelude to creation, but a transitional phase, a cosmic reset where the echoes of one reality faded so the potential for the next could awaken. The great cosmic story is not a linear journey from a single beginning to a final end. It is an infinite loop, a majestic, endless cycle where every ending is a new beginning, and the deep, dark night that gave us life is a recurring, necessary sleep in the life of the cosmos. We have journeyed through 30 incredible theories, from the well-established pillars of cosmology to the wild frontiers of theoretical physics. Each idea reveals that the cosmic Dark Ages were not an empty void, but a dynamic and complex era where the fate of the cosmos was being decided in the dark. The slow pull of gravity, the invisible architecture of dark matter, the explosive death of the first stars, and the possible whispers of phantom particles all played their part in a grand, silent symphony that culminated in the brilliant dawn we inherit. This was not a simple pause in the cosmic story, but its most crucial and creative chapter, a period of hidden construction that set the stage for every galaxy, star, and planet that followed. The search for definitive answers is far from over. It is driven forward by the piercing gaze of telescopes like James Webb and by the brilliant minds of scientists who decode the faintest echoes from the dawn of time. Every new observation has the power to topple one theory and elevate another, bringing us closer to understanding our ultimate origins. So we leave you with a question. Which of these possibilities resonates most with you? Do you believe the darkness was first broken by the gentle, eerie glow of dark stars, or was the foundation laid by a cosmic gravel of primordial black holes? Perhaps you are drawn to the elegant ripple of baryon acoustic oscillations or the mind-bending concept of a cyclical universe. Share your thoughts in the comments below, and if this journey through the cosmos left you wondering about other great mysteries, be sure to subscribe for more deep dives into the universe's greatest secrets.